So now we have to explore what's happening in dimension 3, where we are in space, so the space isometries. And again, very similarly, we will have a theorem that states what this matrix looks like, except that now it's going to be in some adapted basis, in some adapted orthonormal basis of R3. Okay, we have already seen matrices that were isometries. I'm thinking about the orthogonal symmetries that we studied last time in R3. They didn't look like this, although we could prove they were orthogonal symmetry. So again, the idea is in some adapted basis of R3, we will find that it looks like, well, let's have a look at what we have. We have one part that is absolutely similar to what we had earlier. It's a cosine, a minus sign, a sine, and cosine, okay? And so in both cases. And what's the difference between the two cases is that we will have a plus or a minus one. So we have a direct isometry if we have a plus one, and we have an indirect isometries when we have a minus one. Okay, so let's work on this idea. Okay, we will prove all these properties. All right, so let's assume that I want to look like to look for what is my matrix. Okay, to prove that we get those kind of representations. All right, so let's start with this. Let's assume that F is a linear isometry of R3. Okay, so F belongs to R3 of R. All right. So, in other words, it is represented by an orthogonal matrix. Let's call M its orthogonal. Its matrix. Okay. If it's an isometry, we know that I'm looking for some information about the eigenvalues. All right. So, what do we know about an eigenvalue? It's going to satisfy M V for eigenvector is equal to lambda. Okay. Now let's work on the fact that it's an isometry. If it's an isometry, you know that we also have that it preserves the distance, it preserves the norms. So in particular, I will have this mv, scalar mv is equal to, well, the norm of mv square. mv square, and if v is an eigenvector associated to eigenvalue lambda, it's going to be equal to lambda, absolute value of lambda, or norm of lambda, by the way, times norm of v square. Okay, and so that if that's for any time an eigenvalue, but we know that if we have an isometry, that should be equal to v scalar v, right? So which is equal to the norm of v squared. So again, we get absolute value, or I will say modulus of lambda is equal to 1, right? So, well, there should have been a square here. All right, so all eigenvalues, if I accept complex eigenvalues, all eigenvalues have modulus of 1. Now let's study the characteristic polynomial. Okay, what does it look like here? We have a matrix 3, 3, so it's a polynomial of degree 3. So what are the possibilities if I'm considering complex roots? So I've got 3 complex roots, 3 roots, okay? And some of them can be multiple roots. So, and I know that they all have a modulus of 1, so, and that their product is going to be equal to 1, if you remember that, the determinant is equal to the product of the eigenvalues. All right. So what are the possibilities when I've got three roots, right? You know that if I've got complex roots, they never come alone. The complex roots come by pair, and if I have one complex root, I know that its conjugate is going to be a complex, is also going to be a root. So if I've got one complex root, I've got two complex roots. If I've got three roots total, it means that if I've got two complex roots, I've got two complex roots plus one real root. So one of the possibilities is I've got three real roots, of course, okay, or one real and two complex, okay. These are, and if I've got complex roots, it's going to be conjugate, and it has modulus 1, so it's going to be ei theta and e minus I theta, okay? And the real root is going to be 1 or negative 1. If I've got three real roots, you know, it should be 1 or negative 1, and some of those have to be multiple roots, okay? So, very good. Excellent. The case where we have the three real roots, this one where I've got the diagonal matrix is going to be a 1, 1, negative 1, or maybe 1, negative 1, negative 1, or negative 1, and so on. Okay, this corresponds to the orthogonal symmetries that we've already studied last time. Okay, so what's interesting here is going to be, so this case we've already studied that. So and we knew that one special case of orthogonal transformations in space would be the orthogonal symmetries. And now I can consider the other case where I've got one real root, which is going to be plus or minus 1, and some complex roots, which are going to be ei theta, e minus I theta. Okay, all right. So let's work on that. So let's work on that. Let's say that I've got, so I know I've got my, so I've got, let's choose the case of direct isometry, right? Direct isometry. I have one real value, which is 1, and 2 ei theta, e minus I theta. Okay, all right. So let's see. I know then that the eigenspace associated to 1 has dimension 1 because I've got three roots, okay? Three distinct roots. So the eigenspace associated to 1 has dimension 1, so it's spanned by, let's call that V1, I don't know, say something, right? And then I know that I can create E1 orthogonal, and that we know from the orthogonal complement of E1, and I know that E, well, which happens to be R3, is going to be the direct sum of E1 and its orthogonal, so that I can find an adapted basis where I choose as the first vector V1, okay, and two other vectors, something else, right? And some in that adapted basis, so I will have V2 and V3, so which would be basis of E1 orthogonal. But what's important is that in this adapted basis, my isometry would look like, well, you know what it looks like. If it corresponds to eigenvalue 1, I know that I can find f of V1 is going to be 1, 0, 0. Okay, and f of V2 is going to be 0 times something times V1 because it belongs to the orthogonal complement and something here. So I will have actually a block like this, all right? I know that if I choose this adapted basis with V1, the spanning vector of corresponding to eigenvalue 1, and V2, V3, the complement vectors in order to make a basis of R3, I will get that sorry, this is the kind of block matrix that I get, right? And if you work on that, if you compute this stuff, if you work on this expression, if you call this m, you can find out that mt times m is equal to the identity. And actually, what you find is that uh, you will get exactly the same. In order to get mt times m is equal to the identity, you will get on that block exactly the same requirements as the one we found earlier, okay, in the previous case. So that if you've got this part should correspond also to a direct isometry, but in O2. In dimension 2, because I've got only those two vectors. All right, so what does it look like? It looks like a 1, 0, 0 that I've got here, and I've got the direct isometry part from earlier, cosine theta minus sine theta, and cosine theta. I know that there exists some theta in R such that this is true. And so what does it represent? How can we interpret this geometrically? Well, geometrically, so you've got your direction, let's make it like this, your direction that corresponds to eigenvalue 1, that's the one. And so that the orthogonal part to that one, that's going to be E1 orthogonal, okay? And so, yep, that's it. And so, in that, what does it mean when we take, so when we apply this stuff here, let's say that we've got a point x, and again it has that part x1 and that part x2. All right, when we apply this matrix, what's happening? The x1 part remains, right, while the x2 part, is under the influence of this transformation. And you remember that this corresponds to a rotation of angle theta. All right, so I'm moving this. Well, let's take a big angle so that I can represent that better. Let's say that this is angle theta, right? So I'm doing a rotation of angle theta of that x2 part. Or we can say I've got my axis of rotation, which is that, and I'm rotating, then if I'm considering that, so that's going to be m times x happens here, right? So we have a rotation of angle theta along the axis determined by the vector correspond the eigenvector for eigenvalue 1. Okay? Finally, we have to find about that theta. Okay, so how do we find theta? The thing is that if you remember maybe I don't know if you know about this, the properties of the trace of a matrix. The trace doesn't depend actually on the basis where you express this transformation, so that the trace of this matrix is the same whether you choose an adapted basis or not. So if you choose this adapted basis here, the one where you've got this representation, the trace of m is 1 plus 2 cosine theta. So that cosine theta is given by the trace of m minus 1 over 2. And so you can use the arc cosine to get an idea of which theta you have. All right? And the trace, of course, is calculated on the original matrix, which is not expressed in that adapted basis, but as it is constant, you can use this result of the trace. And finally, you still have to find the sign, okay? Because you know that if you use the arc cosine function, it's giving you, so you've got the arc cosine function, if you've got some cosine, it can be plus or minus this angle. Oh, that's an ugly drawing. Okay, so next video to find the sign of theta.